Okay, well, welcome to the ground penetrating radar application in sedimentology. I will take you today from land surfaces down to the lake floors. And okay, now first thing is that, now it works. Okay. Well, it's always an issue what this very general topic is, what I want to say and what you are interested in and what is the relevance. So I start with some different environments, how GPR can help to investigate those with glaciers and with alluvial fans. I will take you to the desert of Saudi Arabia. I will bring you to the subsurface of Rwanda and then on a ship for lake surveys. And finally, I dive down with you to the lake floor of Lake Constance. And the talk is organized like a sediment routing system, so from source down to the sink. To increase the relevance a little bit, I will talk at the glacial environment about how GPR can contribute to quantify global warming, how to quantify with GPR paleoclimate data. Then in the desert, fluid flow is quite important. And of course, some economic aspects with ore prospection in the mine and lake dynamics with a ship. And finally, when we dive, I will talk about archaeological sites. So hopefully there is for everybody something in the talk, so you don't need to dream and you probably will be happy with these topics. But let's start. I'm pretty convinced that not everybody is familiar with GPR, so I quickly introduce the method. We have an antenna, and this antenna emits short electromagnetic pulses, and they are reflected on boundaries. And we have amplitude over time, what we record. And the strength of the amplitude, we color code with dark colors for strong amplitudes and light colors with weak amplitudes. And if we drag the antenna over a certain distance, we add these pulses and these traces, and we can follow and trace with these amplitude, strength, these reflectors. So you get color bands following the shape of the reflector, which looks like this example. So the reflector is somehow the structure, and that means we can reconstruct the depositional history, but we cannot detect the materials which are in the subsurface. This GPR method has the highest resolution of all geophysical methods, which makes it very suitable for sedimentology. And it works also when these lake sediments, where we go later, contain gases. So these acoustic methods like seismics have sometimes problems with that. Okay, well, the boundaries, we get reflections when the dielectric permittivity changes. So this is a geoelectrical property. And if you see granite, clay, sand, salt, limestone in dry conditions, it's more or less always the same. So you can expect only very weak reflections or no reflections even. But look at water. Water has AT. So water has a very big influence on the reflection of GPR. So in the end, we dominantly see only differences in moisture content. Well, please keep that in mind. I will come back to that point later. But now starting with the glacial environment, so how GPR can contribute to the structure investigation of glaciers. And this is a result of a glacier survey. And we have the distance in these GPR sections always on top. And we have the time, so how long the reflection travels two-way down and back. And if you know the velocity, you can also calculate the depth of the GPR section here. And you may recognize already that the glacier base is well recognizable here, down dipping. And also you may recognize internal structure of the glacier, like these boulder nests or internal layering where boulders accumulate. So GPR works quite well on glaciers. And if you tie this GPR device to a snowmobile here, you can do even kilometers a day. And that is very nice to map the base of these glaciers. And in the end, you can create these maps of a glacier base. And with the surface, you can calculate the volume of glaciers. And that's how GPR can contribute to the global warming discussion, because if you have the volume of an ice body, you can repetitive survey the surface and calculate for each year the shrinkage of the volume of the ice, which is a very nice data set for this global warming discussion. Well, then next topic, I promised to go with you to the alluvial fans here in Switzerland. The alluvial fan, they act as a climate archive, and GPR can contribute when you go with, for example, 50 kilometers on this Illgraben fan, spider net-like GPR survey. And then we had also detailed 3D grids, and they contribute also with another 25 kilometers of GPR section. So really large surveys, and we can combine these large surveys with outcrop data. So we have our sedimentological section, we have the lithophases, some measurements, whatever you like when you have outcrops. And if you go with a GPR over that outcrop, you can also detect certain layers, fine-grained layers, for example, here. And you can trace channels in the background, and you can trace, for example, these fine-grained layers. Please keep that in mind, because I come back later to these very special horizons where fine-grained sediments occur in an alluvial fan environment. So when lithophases meets radar phases, we can go for 3D and trace these very specific horizons. We can trace the channels, we can attribute everything, and we go for 3D. So this is a 3D survey, one of these grids, and we can densify the grids by perpendicular surveys. And at the end, we have a full data cube, but don't worry, I will not introduce all the data. We will jump in this special part here, smaller part of the big grid. And this is what we can do. For example, here is a channel. Base is a little bit weak, but we can map this channel and in a 3D modeling program like GoCAD or Petrel. And then we can reveal the sedimentary architecture of these alluvial fans by following these channels, following other architectural elements. And so at the end, all these architectural elements are fully attributed because we know the lithophases from outcrops. We can measure something, we can take samples, and geometry, directions, dimensions are quantified with the GPR surveys. Then we can form depositional units. We can investigate the depositional history of these fans, and ta-ta, we have trends in these different units. For example, stream flow deposits versus debris flow deposits. And of course, these trends are a paleoclimate signal. Now I come back to these paleo surfaces, these fine-grained horizons here. And this is how they look like. And they have a volume in between. And this volume, of course, can be quantified with the 3D CPR survey. This is how they look like. They have charcoal and also initial soils, bleaching. And the good thing is the charcoal layers can be dated by C14. So we have a volume in the age model, a volume age model. There's the age. This is the volume, the sediment yield per year. And in this case, in Switzerland, Engadin alluvial, Samaden alluvial fan, we have a very short period of almost 8,500 cubic meters a year that increases in the next period. Also still very high in the third depositional unit here. Then you have depositional starvation. Then it is reduces again, depositional starvation, and then a very small sediment yield in the last unit. And if we compare that to a paleoclimate data, for example, here, this is the glacier movement today. Then this is the little ice age. So to the right, it's getting colder. To the left, it's getting warmer. And we see that all these sediments are deposited in cold periods where permafrost is melting here. And this is the paleoclimate signal where we mobilize the sediments on the alluvial fans. So GPR and of course C14 dating can contribute to quantify and predict what happens when permafrost melts. But it's also not a temperature signal. So I take you to Peru now on another alluvial fan where we also had the little phases, we had GPR surveys, we had C14 dating, and we can have climate data. This is moisture in this time. And the moisture is for today, this black line in the middle. And we have periods where it's drier than today and periods where it's more moist than today. And ta-da, again, all these sediments of this alluvial fan in Peru was deposited in moist phases here and here compared to the modern level of moisture. So again, moisture, temperature, paleoclimate archives are very well developed in alluvial fans. And next topic, fluid flow, arid environments. So this is the desert of Saudi Arabia. And in the desert, we have dunes, and sedimentologists like dunes, of course, and very nice features. And we will see a GPR section running from roughly here to this point. And well, very nice deep penetration. We see the base of these dune fields and these different dips of these faucets. We can interpret them as this is a star dune. So sedimentologists love these GPR sections and dune fields. But please remember that point here between 40 and 50 meters in the middle of the section where these inclined faucets are. And we did some fluid flow investigations here. And maybe this is the secret below that plate where we go with a GPR over that plate. And I lift that secret for you, what is behind. Wow, it's a double ring infiltrometer. And we want to know how much and fast can rainfall contribute to groundwater recovery. And now remember what I told you at the beginning. GPR is very sensitive to water, so that should work. And we used a double ring infiltrometer. And of course, no metal parts should be inside. So there was a metal-free double ring infiltrometer. And this is the result. And you see here that the water is going down. I marked the hyperbola, which is the front of the water in red. And here, these are the dune faucets, the inclined dune faucets at the big section between 40 and 50 meters. And the water infiltrates here, and then it goes down. And you see now that the middle part, the inner ring, goes a little bit faster than the water in the outer ring. From this data, you can calculate infiltration rates. You can infiltrate the velocity, K values, whatever. This is another example. I let it run in color that the water is infiltrated here and then it went down. This is, in this case, a water pulse only for 5 minutes, and the water pulse, the waterfront goes down into the subsurface. This is another example, and I need to start it. And here you can see also the water running down. The water pulls into the subsurface. And well, in the end, you can also do that in 2D. So not only a point source, you also can irrigate a whole line. And this is what we see now in a also a little video that the water is going around local aquitars. So there is a preferential flow along that line. And okay, I need to click on the film. And this is the result. You see that the water is going down here first, and then it got stuck here. And then the water in this part overturns the water here, and preferential flow develops along that 2D line. Maybe I show it again to you without comment. So you see the water along that line running in the subsurface, and there is preferential flow. So it's not the same velocity in all parts of this line. So very nice for hydrogeology. And you can do also this in 3D. And if you take the time also as a dimension, you can do a 4D monitoring of the preferential flow and irrigate in 3D and get models in 3D here, how the water is distributed in the subsurface. Okay, well, now I take you to the subsurface of Rwanda in a mine where cassiterite is prospected. And we work also in 3D in the subsurface. So you can go with a GPR along the mine shafts on all sides of the wall. You can go in the tunnels, in the ceiling. Yeah, you just take the GPR at the wall, at the ceiling, at the wall, or a little bit boring already at the floor, standard application. And you also can go on the surface, on the hill where the mine is located, and do your GPR survey, your grid, for example, here. And this is the result. The cassiterite is in veins, and around the veins there is laterite. And GPR does not work well in laterite because it has a high conductivity. High conductivity kills the radar signal. So we have a no signal area, large no signal areas, but we are not interested in laterite. We are interested in the veins, which were nicely visible in the GPR section and in these pockets, weathering pockets where the cassiterite is accumulated. And we have placer deposits in a paleo relief where the ore is accumulated. So we can locate areas where the veins are or where placer deposits are. And with this information, the mine could increase their production 3 times, which is also an economic factor for the country and of course also for the local company there. Now I take you to the lake. And so why investigating lakes with GPR? Well, humans interact with sediment fluxes, with sediment distribution processes in the littoral area by changes of the coastline, for example. They interact with construction of flood protection. So in terms of Lake Constance, the Rhine Delta was completely shifted to another location. We need channels for ships, for example, and well, that leads to accretion or erosion when sediment fluxes are changed. And in the end, if we want to regulate something, how can we do renaturalization without running into problems with erosion or running into problems with accretion? Well, this underwater GPR now was developed in a BMPF project, this one. And well, we started from the surface, of course, make it easy. We put the GPR in a boat and we direct that boat from the coastline into the lake and see what happens. And this is the result. Well, not bad, but there are some issues. However, the consolidated lake floor is pretty nice visible. There's some mud accretion on top with very weak reflections here and here. There are a different level, a different wave level recorded here. So a sunken coastline here. So not bad, but there are also some issues We have, for example, waves, yeah, of the surface, which when the boat is moving up and down, we have this also in the data here. These are the waves. So we have multiple reflections, and the penetration depth, well, this is also a formal coastline here, but the penetration depth, you see, okay, from 1.5, 2 meters onwards, we rarely or we weakly can penetrate the sediment here. So for a sedimentologist, this is a little bit just frustrating, because we really wanted to see more of the sediments down here. So we have to go diving with our GPR. And this is the education pool of TU Darmstadt. You see our first prototype. We did first tests here. And well, this is our technician, Raimund. This is our first prototype. And you see the prototype is breathing. There are air bubbles. Our technicians is not breathing. So there is still some homework to do. So we have to make him breathing and sealing the antenna. But one day we can go for advanced test, and we use the diving tower of the fire brigade in Frankfurt. And this is very convenient. I had a platform to assemble the device, and then we brought it down to 12 meters water depth, and ta-da, the antenna is sealed. No water enters, no air comes out. So we were pretty sure that we can go for field tests. However, field is another thing. We had really problems with macrophytes, which go into the system, which block the system, with sediment going on top of the device and so on. And several times I have to dive down to rescue our system. So it was hard learning, hard way to develop a system in the end, where we can go for the big survey and to have it ready for using subsurface. So this is with a big ship, Cormoran, and I'm very thankful to the Institute of Lake Investigation, the Institute for Seenforschung in Langenargen, especially to Martin Wessels, which helped us a lot with his ships and his expertise, how to use submarine equipment. And this is our device. This is a sledge using it, and we have a survey wheel for controlling the system, and we have for underwater positioning a boat with a GPS survey on top. And in the end, you will see from the GPR only that GPS boat and the buoy where we can bring in the system and take it out from the lake. So the rest of the system is submerged in the water. This is how it looks like in the littoral zone. And this is how it works. Now it's recording data with the survey wheel, the system to pull and transfer the data, the system to take it out from the water, and this is the system to keep the GPS positioning over the unit. So these are the results. And what you easily can see that the quality is much better than in the survey from the boat. There is a channel on top with erosion on former channel sediments, which show a oblique infill, and there is delta deposits running from here down to the lake. And if we shift that section a little bit, you see this is 100 meters here, another 100 meters. The delta sedimentation continues, small channel here. Then here at this part, there is another lake level recorded with onlap on this part. There are some boulders or some obstacles. And so this is really nice quality, what sedimentologists like to reconstruct the depositional history and sedimentary architecture of the littoral zone in the lakes, and to reconstruct the sediment fluxes which occur here. Another example is these mysterious sand waves in the littoral zone in the Rohrspitz area of Lake Constance. And this is the result. We did a survey here, and these sand waves here on the surface, they continue in the subsurface, which we haven't expected. And so I think there are a lot of sedimentary structures still unknown in this littoral zone, because now we have the resolution. and we have the penetration depth of the underwater GPR to reveal what's really going on in these littoral zones with the sediment distribution here. And also channels, submerged channels, so paleo channels, they show a completely different architecture than fluvial channels, subaerial fluvial channels. And this was really a little bit astonishing for us and shows the potential of that device in the littoral zone of lakes. Well, in the end, I will talk a little bit about archaeology. And in 2015, 170 boulder mounds were discovered along the coastline of Switzerland. There is Hornung. And in the end, all these 170 boulder mounds comprise a volume of 80,000 tons of material. So this is quite significant. And the survey with a echo sounding device here revealed that they are circular shaped, and they are 1 to 1.50 meters high, 30 meters in diameter. And that was really a mysterious thing. And the question was, is it archaeology, so man-made, or is it geology? And so the thing was that the sediments, which are here at the lakeshore, are deposited definitely after the Pleistocene. But however, the hügelis could be the top, so the summit of a moraine, or are the hügelis, which is the local language of Switzerland for these mud, the boulder mounds, or do they sit on top of the sediment? Then they would be man-made. And perfect for underwater GPR survey here on the hügeli. You see these boulders, and this is the result. So we found the glacial moraine at the land side, 150 or 50 meters away from the land. So the glacial moraine is submerging here and dipping down here, continues down there. So sediments here are on top. You see different radar phases, weak reflections, strong reflections, and weak and strong reflections combined with some chaotic layers in between. So completely different radar phases. And then the hügeli sits on top of the sediments. And I will also zoom in here now. There is also a tail of these boulders which were rolled or fallen down the former slope of the lake. So at the time when the hügeli was built, it was exactly the transition from the littoral to the sublittoral or even the profundal here. So these sediments were not there already. They come later and covered these fallen blocks. And then if I go back, the sedimentation continued here for quite a long time after the hügeli was destructed or destroyed. So this was amazing results, and therefore we could state that the hügeli was definitely an archaeological phenomenon, and it was integrated in the sedimentary record. And because the sedimentation continued, it must be very old, so at least prehistorical time. Well, archaeologists were alarmed, and they did an underwater excavation, and they found wood poles below the hügeli in the sediments, which was predicted that they continue here. And the C14 dating revealed 3,400 to 3,900 calibrated C14 age before Christ. So that was Neolithic age. So what we expected from the GPR survey was proved by the dating. However, some people argued that the pole was hammered after the construction of the hügeli through the hügeli, and that means we need to drill. And we have to date the sediment above and below, for example. So GPR is very nice to go for exact drilling locations so we can hit these layers and date them. And so that was done here with the layer where the blocks fell down or rolled down along the hügelis. So we do the sediment dating here, which gives us a minimum age of the hügeli. And that was the survey, that was the sample, lake sediments. The sample was taken here with such a floating platform. And thanks to Flavio Anselmetti, he did that survey here with his group. And we extracted these organic materials, and the dating said again 3,500 to 3,700 years calibrated before Christ. So the sediment proved the pole was hammered inside the hügeli when the hügeli was constructed. So that means we are in the Neolithicum between the Pfühner and the Hornung culture, which is a time gap in archaeology, and it was very spectacular. So that was a really big medial echo. So newspapers were reporting about these hügelis, the poles, how that could look like. And they also reported about a GPR survey. And I see that we have still a few minutes time. And if you wish, I can show you a film now for the end to relax a little bit from the Swiss Evening TV. And it's in Swiss language. And also I will talk in the Swabian dialect. So some of you may be not able to understand something, but you nicely see how underwater GPR works. And so I suggest, if you do not insist, that I show you that film of the Swiss TV. So this is the film. Could you see that picture? Okay. So then I started, and I do not make any comments. Maybe you are able to understand the Swiss dialect and the Swabian dialect. And if there are any questions, we can talk about that later. Okay. Ah, ja.
Sie beobachten unscheinbar Ablagerungen von Bodenbeigletschern vor etwa 50 Jahren. Oder bei Menschen Steine verschwinden. Speziell, wenn gestern exklusiv über die Untersuchung von diesen Steinen von dabei sind, werden wir gespannt sein, was ist. Das Forschungsschiff Hornung in Stolzen und Landesarchaeologie vom Kanton Zürich jetzt für die Zeit in der Situation. Aber täglich zwei Monate stehen sind, und hier in der Volumetric bleiben. Gut 4 Meter unter Wasseroberfläche angeordnet in einer regelmäßigen Reihe. Die Unterschiede haben eine Durchmesser von 15 bis 30 Meter. Entdeckt in den Jahr 2015 wurde 40 Meter vom Bodensee. Jetzt kommt ein archäologisches Messung herausgefunden, dass sie durch Gletscher oder von Menschen entstanden. Jetzt sehen wir genau die Unterschiede. Jetzt sehen wir da Georadar im Wasser, das Lüsten in dem Rad, hier sind die Durchgehende und dann fahren wir Oberflächen ab. Und damit wir diese Möglichkeit haben, den durch das kleine Größe, wo das ganze Geometrie reflektiert. Geht mit dem Rad voran. Das ist die Sedimentologie Hornung, die Hinsicht der Verknüpfung entwickelt. Es ist zweitens erst im Wasser funktionieren der Radargeräte. Es macht einen Unterschied im Boden. Es ist extrem spannend, dass diese mit dem neuartigen Gerät unter Wasser der Georadar zu machen. Ja, das ist spannend. Mit dem Motor ziehen sie das Radargerät über den See. Messdaten werden über den Satellit im Bodenboot der Computer vom Geologen benutzt. Wenn wir das über den Untergrund führen, dann werden wir Lehrer so eine Messung machen, das regeln und kann. Dann können wir so eine Art Schnitt erklären. Dann spüren wir davor aufschneiden, und man sieht, wo da diese Schichten verlaufen. Plötzlich kommt der Radar nicht mehr richtig.
Ja, probieren wir mal, ob ich der bitte anhebe, wie ich halt da was, kann da mal überlegen, so dass ich noch bleibe. Ja, ich weiß nicht, okay. Was? Also, oh, da können wir mit, okay, da können wir nicht reden, Frau. 10 Minuten ist überwunden. Jetzt muss der Rat ausschließen, über eine Stelle wieder zu bereiten. Und die Forschungsschicht wartet, die hat die Notdurchsetzung und gestaltet Resultate der Messungen und der Klarheit, die wir heute ausziehen. Wenn das natürlich so abgeleitet wird, dann müssen Sie sich das vorstellen, wie grundsätzlich das geht. Zwar fällt man an und überall. Es ist ein Abend, dann hat man die grüne Seeablagen, die grünen Zahlen. Und der Mensch hat den Gestein in einer späteren Zeitpunkt nachgewiesen, in Wasser oder andere Unternehmen Pflanzen. Nach ein paar Stunden ist der Verwaltungsmensch, die wirklich jetzt und die Stunde der Wand. Das ist vorher, oder? Dass man Menschen finden, die in regelmäßigen Abstand angehalten, an der Darmstadt gehalten, Gesteine demonstriert. Also es ist eine Situation, wo man 900 Meter Gestein ablagert, was das ist. Gibt es herauszufinden. Steine, die können Sie gut zwischen 5000 und 5000 Prozent Palaeoclimate sind. Wieso? Das liegt an Archäologen, die immer längere Zeit beschäftigen. Aber neben steht Wissenschaft, wenn einer von diesen Steinen noch knapp ist. Okay, so time is also over, and I would like to end up here. Thanks for joining my talk today, and I love to answer your questions.
Yes, thanks.